designing, manufacturing, installing, and maintaining the high-speed electronic computer, the largest and most complex computers ever built.
Hello, everyone, and welcome to the Building Better Systems podcast, where we chat with people in industry and academia that work on hard problems around building safer and more reliable software and hardware. My name is Chapman.
And I'm Joey Dodds.
Joey and I work at GAWA. GAWA is a research and development lab that focuses on high-assurance systems development and broadly hard problems in computer science.
And today we're going to be talking with Rod Chapman. Rod's had an ongoing involvement and an influence on the Spark Ada community, where he's helped develop both tools and proofs in that ecosystem. Rod's applied formal verification to some really important systems, and notably, he's done that really practically and cost effectively. In this episode, we're going to talk about how Spark Ada has been used to correctly implement critical systems, such as air traffic control software. And we'll also talk about just how successful those efforts have been. Rod will go ahead and explain some of his more recent effort verifying TweetNACL, also in the Spark Ada ecosystem. TweetNACL is a tiny implementation of a cryptographic library, so it's very complex. He'll also explain how he was able to use Spark, a tool which was traditionally intended for primarily proving correctness. He'll take Spark, but he was actually able to improve the performance of that TweetNACL library once it was compiled.
And just a side note for those of you who are watching the video, this conversation was recorded earlier in the pandemic when trimming my beard somehow became optional for a while there. So please excuse the caveman look.
Thanks for joining us, Rod.
Okay, thanks for the invitation to join you.
So we'll start off with our normal question, Rod. What is your approach to building better systems?
Well, that's a good question. My background is in building mostly safety and security critical embedded systems. For many years, I worked for a company that used to be called Praxis here in Bath, is now called Altran. And I work independently at the moment. But I guess the company and the approach was I guess best known for its what I would call a sort of pragmatic approach to formalism, where we were known for trying to apply more formal methods to system development. I mean, it's all rooted, I suppose, in a really trying to do a mature approach to requirements engineering for particularly safety and security, trying to get that non-functional stuff nailed early in the project.
Your approach to building better systems starts with specification.
Indeed. I mean, requirements engineering and specification is fundamental. If you're going to build something right, you've got to know what it is you're trying to build, and possibly more importantly, why you're trying to build it. And the other thing that we find is very important is understanding the domain knowledge, is trying to formalize and write down all the assumptions and sort of tacit knowledge about the operational environment of the system, because very often people get that wrong, and then systems fail when they hit the real world, as it were. You find out you've got something wrong. And that's pretty difficult, and that involves a lot of work in validating that stuff with real system engineers and users and so on.
Yeah. There's a few things I want to dive into there. One is that you represent this idea, and this is going to maybe seem surprising to some people, but you represent this idea of we're going to start with formal methods and build in formal methods from the start, including mechanical specifications, including even things to check these specifications. And to consider that pragmatic might seem surprising to some people who think of formal methods as something that's expensive and unreasonable to apply in most production settings.
Yeah, in other words, this sounds very expensive, Ron. Sit down, write all the domain knowledge, write the technical specification, and then start working. I mean, we got stuff to do here.
Yeah, it's a fair point, and it depends on the system. It depends on how long we've got.
Well, and to be clear, I'm being facetious because I know you've actually managed to accomplish a lot of things in real systems with that stuff. So I'm curious about your take on that.
It's clearly this kind of approach is perhaps not appropriate to very fast moving industries. If you want something out next month, this may not be for you. But typically we're building systems which take a fair amount of time to build in the first place, but also systems which are going to be around for 20 or 25 or even 40 years. If we look at long-lived embedded systems in the nuclear industry or the rail industry, these things have very long lifespans. So actually taking your time to get them right is okay. And so for example, on the certificate authority that we built for the Mondex system, we probably spent a year doing requirements engineering and formal specification work before we wrote any code at all. And that was formal requirements, formal spec, and architecture design, basically, sort of building a bunch of stuff so that we knew it was going to work and we understood what we were building. We probably did about a year of that before we got near writing any code. But that system, when we built it, it was designed to have a lifetime of 20 years, maybe. So that's not outrageous. I mean, it's also worth saying that the team that are doing the formal specification and requirements work is actually quite a small team in comparison to the overall size of the project. That formal spec work might only be 10 or 15% of the budget for the whole project in terms of people and time. And it's okay to admit that those people are particularly skilled at what they do. They combine a very interesting skill set, which is the ability to do requirements elicitation, to actually talk to people and resolve conflicts and kind of eke out this domain knowledge stuff from the background from users. And also the ability to write it down formally is a very interesting combination of skills. So these people aren't, easy to find or train, but they exist. But you don't need a huge number of them. I think we found, as I said, it's not like everybody on the project has to have that skill set, and that's okay to be in that kind of mode. It's appropriate for some projects, certainly not for all, and that's perfectly reasonable and pragmatic, I think.
Well, it sounds like, when you're done with these things, you can really sleep well at night because you've done everything to make sure that these things don't fail.
Yeah, we hope we get it right. And clearly, I mean, perhaps another myth with this is that people say, "Oh, well, our system's going to change, and we have to cope with change, so we can't do formal methods." But we don't find that's the case. The formal specifications we found over the years are as amenable to change as much as any other notation. And of course, this stuff changes. We don't write it down once and then it's all perfect. That never, ever happens. And of course, we iterate. We do incremental style development, just as is common on all projects. And this formal stuff does get updated and changes as a project goes along, as requirements change and other things change. But we don't find this material any more difficult to change than any other. And it's sometimes easier to change than code, for sure, because the formal material tends to be a lot more concise than source code. So we maintain these design artifacts throughout the lifetime of a project, just as you would with anything else. I'm just a bit worried. There is a persistent meowing in the background because my cat's trying to get in.
We can't hear it.
Should I let the cat in or not?
That's up to, well, that's dangerous. Having a cat, I think that's dangerous. But
it always happens in these conversations. The cat will invade.
That's part of why Spot's in the office, right?
That's exactly right. I was going to say.
His cat's only trying to board the bus right now.
Yeah.
Okay. Well, let's press on then.
Yeah, it's completely up to you.
Okay, fine. I think he's gone away. So let's press on.
So to summarize what you said, basically, you've worked in this environment where at the outset of the project, a small team of reasonably expert proof engineers, in some sense, specification engineers, I guess, because they're not even doing proofs yet at this point. Architects are setting out to understand the goals of the project and the knowledge necessary to undertake the project and to record that in a precise mechanical language, basically.
Yeah, that's a reasonable characterization. I think it's worth mentioning as well, with reviewing this material, we do have experience of we have taught customers to read the formal specifications. And the skill set you need to read this stuff and understand it is very different from the skill set you need to be able to write and construct this stuff. So we have different training courses, for example, for reading and writing a language like Z. And we have successfully trained customers. On another big project that we'll probably come on to, part of the UK air traffic control infrastructure, we trained air traffic controllers to read Z so that they could check what we were writing and say, yeah, that's what I want. Because these people the buck stops with the air traffic controllers because they're the actual users. So we trained them to read the spec, to validate with them that what we were writing really was what they thought they were getting. And that's possible. So teaching people to read this stuff is okay. And even a notation like Z, which is famous for being rather it's a tricky notation, shall we say. It's not perhaps the most readable notation in the world. It's certainly possible.
Yeah, I'm not familiar with Z. Could you briefly tell us about it?
Z is a formal specification language for particularly excels at functional behavior. It's based on basic maths. It's set theory, relational algebra, and functions with a kind of overall structuring mechanisms called schemas. But it does use a particularly mathematical notation. It's very concise, but there's an awful lot of mathematics. It looks like maths, and that tends to put people off. It is very, very powerful in terms of what you can say. Its expressive power is very high. It is perhaps held back because of its very expressive power. Tool support for it is not as advanced as we would like, which is a shame.
But it sounds like you got non-experts to read it and to compare it to essentially what they do every day. How was that?
I think that worked reasonably well. As I said, I wouldn't describe these people as non-experts. They are not software engineer experts, but they're experts at air traffic control. And that matters because these people really are the domain experts about how they work, how they actually do their job of controlling aircraft above the UK. They are the domain experts, and that is crucial to access their knowledge, to get them to understand what we're proposing to do and what we're proposing to build. So they have an enormous role to play, and was really, really important in that project for sure. Otherwise, we'd produce something that was all formal and beautiful, but they wouldn't use it and they wouldn't actually accept it at the end of the day. So it's really important.
Yeah, so I think it's implicit in a lot of what you're saying is this idea that you can take something and experts can produce it, in this case, this formal model. But then a lot of other people need to be and can be able to consume this stuff, because also it doesn't sound like just the air traffic controllers in this example were consuming it, but also that the architects are handing off artifacts to engineers that are not as expert in building up the architecture, but that are able to actually do implementation based on these specifications. So that group also needs to understand.
That's right. So we on, say, the air traffic control project, we run a kind of development pipeline where the requirements and spec is being done for 2 builds down the line. A build is being implemented and a build is being tested and accepted. So there's a kind of a 3 or 4 stage pipeline to it. So when the formal spec stuff is done, it gets handed over to the development team. It actually goes in 2 directions at that point. There's a development team that will read the formal spec and implement code, essentially. But there's also a verification team who read the formal spec and, based on the formal spec, do all the analysis to construct test cases and test scripts and validation and all the stuff you'd expect. And that's done by an independent team, if you like. So there are people who need to read that material, and that's a much bigger team. Clearly, the development team, the air traffic control project is called IFACS. So the IFACS development team probably peaked at over 100 people, split across kind of development and testing and verification. So you've got there a pool of about 100 people who need to be able to read that formal notation and either produce, to do the analysis to produce test cases and scripts and so on, or read the thing and be able to produce code to actually implement it. And that takes us into the kind of implementation pipeline. So the formal spec becomes the kind of gold standard, if you like. that it's what the tests are based on, it's what the code is based on, and it's what the users have actually agreed they want us to build. And that's a really important kind of central point of the process, if you like. And then we try and carry on that theme, I suppose, and do the implementation in a formal style as well, where we try and, again, use formal languages and tooling at the implementation stage as we go on towards actual code and deployment as well.
It sounds like that part is useful but not required. In other words, if you do this careful mechanical architecture step, you're likely going to get benefits from that, whether you sort of go prove your implementation equivalent to that or not. You can further the benefits by doing formal engineering as well, but the specs stand alone as a useful artifact that can be used on a software engineering.
As long as the engineering team is looking at it carefully while implementing, right?
Yeah, you could. I mean, the upfront requirements and formal spec work has enormous benefit in just, I mean, we've always said to people, if you're going to have a problem, would you rather have it now or in 6 months or a year's time? Because of the cost of getting it right by fixing a few lines of Z is pretty trivial. The cost of fixing it in 6 months or a year's time and having to refactor thousands of lines of code and thousands of test cases. The cost can be orders of magnitude higher if these things come out late in the process. So it's just standard lean, or people call it shift left, or lean engineering, or correctness by construction, or whatever. This kind of effort on getting it right up front pays off because of knowing that we're building the right thing. The formal implementation style, I think, is interesting because it ensures that we don't drop the ball in implementation by, you can have a great formal spec and then do a hopelessly defective implementation of it that will not satisfy anyone if it just doesn't work. So it ensures that our refinement, if you like, from spec to code is actually strong or sound, or at least the code is free from large classes of common or garden defect that you would expect in software. So where the spec jumps from the mathematics of pure integers, where we jump to a computer and we're jumping into the world of von Neumann 32-bit, signed bounded integers, there's a huge scope there for screwing up, making a mess by, overflowing and all the things we know can go wrong in software. And the formal tools at the implementation level kind of keep us honest at that level. And they also force us to ask hard questions, because when you do jump to a constrained computer implementation in a programming language, the verification tools will say, oh, well, what about there? You might divide by 0. And you think, oh, yeah, I don't know what to do about that dividing by 0. So you look at the spec, and the spec doesn't say. So you go and talk to the requirements people, and you say, what about this case? Because if this and this and this happen, at this point, we're going to divide by 0. And typically the requirements people will say, oh, yeah, we didn't think of that. Well done. Oh, yeah, we'll go and ask the customer. And you go and ask the customer. And lo and behold, you found a hole. You found an incompleteness bug in the requirements. And they can be quite difficult to find sometimes. So the formal implementation style kind of keeps us honest and forces you to ask hard questions, which, again, is a good thing, basically, in general. So it does fill in some gaps where otherwise, defects could fall through the process.
Speaking of the customer, I know you said, this is a relatively small overhead to, go after this specification, kind of upfront cost of formality.
Yeah.
In your experience, what's been, has it been hard to get customers and the end user on board with spending that year or doing that? I assume part of that is, if something's going to be used for 20 years, then like do whatever you need to do. But
it can be a very tough sell if you're talking to a company that's used to very fast moving development, trying to, pitch this kind of approach to them is quite difficult. If it's an organization that's coming to, high assurance, either critical or security related development for the first time, it can be a very hard sell to say, hey, we need to change the way you're thinking about this. in some regulated industries, so traditional industries which are traditionally have a regulatory structure, so typically civil aerospace or the rail industry or the nuclear industry, this kind of approach is more accepted as being the right way of doing things because the cost of failure is so enormous, either in terms of lives or liability or financial damage. And those systems are very long lived. So there are some industries where it's an accepted way of working. Some industries it's still seen as being rather strange, and it can be very difficult, a difficult approach to bring to other businesses. Sure.
So it sounds, yeah. So the regulation seems like a big factor. That help that makes people want to work in this kind of way, and even the cost of lives and the cost of the financial cost aside. In a lot of these situations, it's really hard to even update the code if it's just like a little annoyingly wrong, right? Like if it crashes every so often and it kind of you restart it and you growl at it, even that is incredibly costly to fix that, and you can't do it right away in a lot of these settings, right?
Regulation or regulators are a double-edged sword, if you like. Sometimes they are good and help us to work in the right way, but yes, they are renowned for being slow-moving and creating an environment where it's very difficult to make changes, to a project, because of the cost of having to fix things. Sometimes can be very expensive and time-consuming. And different industries have different regulators, and they have their own way of working and their own way of doing things, depending on which industry or country you're in, and which legal setup. So regulation is a tricky thing to deal with. We'd rather people chose to go down this path because they think it's a good idea, not because they think some regulator's going to hit them with a stick. We prefer carrot, not stick, with this approach to kind of lead people in this direction. Which has worked on some occasions very, very well. And as I said, some occasions we've struggled to bring this approach to bear on industry, but we continue to try. As I said, the company that I used to work with, Altran, is still very much in business and doing this kind of work very successfully. So there's, they've done so successfully for 25, 30 years now. And are still doing it, so that's a good sign. I think that it's paying off, and they're a profitable business, so that's a good thing.
If I'm someone listening to this podcast and I hear this idea of formal specifications and it makes sense to me, and I want to try things out, what are ways that I could do that? The follow-up question is going to be on the side of the people building formal methods tools. Like what can we do to close that gap a little?
So how to get into it? I'd probably advise don't try and get into Z immediately, because it's not the first language to try. I think there are formal spec languages these days, perhaps much more recent contemporary approaches, which have much better tool support, and are more approachable, perhaps are a little bit more domain specific. They are very, very, very good at certain types of problems. So in control engineering, in control theory, there are superb tools. This kind of formal stuff is very well known, as you guys know, in hardware engineering, in building VLSI and FPGA designs and circuits. This kind of formal modeling stuff is just standard practice these days. So that's one industry that's moved in that direction. So there are languages like Alloy, which comes from MIT, which has a nice, easy to approach model of the universe where you can write things, and very good tool support that gives you a lot of bang for the buck. We've got really good tools now, particularly tools that generate counterexamples are just awesome. Because basically you press the button and the tool says, no, it's wrong, and here's how it goes wrong. It gives you a test case or something to say, in this case, this would be wrong. And you go, oh, of course. You get what I call the head slap moment, where the tool says, no, it's wrong because here, and you go, oh, like Homer Simpson, and realize you've got it wrong in a really tangible way. So probably the biggest advance we've seen in tool support in the last few years in these tools is this thing called counterexample generation, which is fantastic. So tools like Alloy are very, very good. You guys have the Cryptol system, which is awesome, but for a particular domain of things like specifying cryptographic primitives and protocols and formats, that's a really, really good system with great tool support. And there are probably other examples out there which are you could cite as well that I can't currently think of. But no, there are ways to get into this kind of thing. And the other thing I'd suggest people try is there's quite a lot of so-called lightweight formal methods tools out there. So tools that aren't promising to kind of prove everything or make some grand statement about your thing or your code. But there are tools out there that will check certain important properties of your code. So, for example, there's something called so-called bounded model checking tools for programming languages like C or Java, which do a great job of finding some of the bugs. They don't promise to find all the bugs, but they're very good at automatically finding some of the bugs and typically giving you a counterexample. They'll say, there's a buffer overflow here, and if you put in this test data, if X equals this and Y equals this, you've got a buffer overflow down there. Those tools are really good. You get a lot of bang for the buck from them without having to do too much work. You throw your code at them and go and get a cup of coffee and come back and see what it says. So they can be pretty impressive, I think, as a kind of entry point for this kind of material.
Then the follow-up question was, and I think in some sense you've answered this quite a bit already, is what can we do for from the tool development side? And I think a lot of what I was hearing is that helping people understand how something like Alloy can apply to their domain almost out of the box is going to be critical, and not forcing a lot of work between a really general purpose tool and the domain it needs to be applied to is a lot of the legwork that we can do on the tool side to help people use these approaches.
Yeah, I think that the technology underpinning the tools has come on in leaps and bounds in the last decade or so with research on theorem proving and model checking and all the underlying technologies. It's amazing. I think perhaps what we need to help adoption, it's more about user experience these days. So we need tools that have a really good, robust experience of the user, a nice user interface. So I say counterexample generation is fantastic. But also just stuff like tutorials and training material, give me an example of how this technology and this tool applies to my application domain, something I can start with and play with and maybe inject bugs. I could try and inject a defect in it and see what the tool says. So material that people can play with to get going, to kind of get over the hurdle of getting into a new tool or a new technology. And that takes effort to produce. I've been there with tools, and as a tool developer, I've been there, and you think, oh, we've got this great technology. Why won't anyone use it? Oh, that's funny. And it's about having the whole package. It's about having really good user experience, training material, tutorial material, online stuff that people can access and support, and all that stuff as well. And that's part and parcel of maturity in the market, I think, for these things. And it's something that you guys have done countless times. I've been there as well, and other companies have been around that cycle.
Yeah, you hit the nail on the head, and we've been hearing that loud and clear, especially over the last couple of years. I want to switch topics a little bit and bring up TweetNACL.
Okay.
I was hoping you could tell us a little bit about that. It's a very impressive project, so I'd love to hear kind of an overview of it from your side.
So yeah, this has been my kind of lockdown project while I've been unable to get out much, and I needed a side project, if you like, to kind of do something while I've been stuck here in my office for the last year. So let me give you some background. TweetNACL is a compact reference implementation of the NACL cryptographic library. It was designed by the designers of NACL, a guy called Dan Bernstein and his colleagues. And the interesting thing about TweetNACL is it's written in C, but it's designed to be an extremely compact implementation of that cryptographic library. In fact, so compact, it was designed that you could actually tweet it in 100 tweets, which sounds like a strange idea, but there you go. As is common with a lot of cryptographic code, there's quite a lot of rather advanced mathematics going on under the hood. There's, all the implementation of this stuff called elliptic curve cryptography, and to make it go fast, there's quite a lot of mathematical trickery going on. Also, it has this rather strange coding style where it's written to be constant in execution time. So the execution time of the algorithms does not vary based on the input data, like the data you're encrypting or the key that you're using or whatever. So this is a cryptographic property that is desirable. That means it's written in a rather weird style. If you read the code, you just look at it and go, huh? What is this doing? Because it's written in this bizarre style. And you think, well, why don't they just put an if statement there? And the answer is, they're not allowed to put an if statement in because that wouldn't be time constant. So I looked at this implementation and I was amazed at how compact it was and stuff. But it's extremely difficult to understand how it works and why it works. So what I decided to do was to try and rewrite it in a formal language. And the formal language is this programming language called Spark, which, by the way, is spelled with a K on the end. And it's not Apache Spark. It's got nothing to do with big data or Hadoop or any of that stuff. We were using the name first like 30 years ago, right? So it's a long story. And it's not Spark with a C on the end either. That's another long story. So Spark is a formal programming language. It's rather odd in that it's a real programming language that you can compile with GCC and run on a real target, but it's formal and we have very strong verification technology for it. We have a full-blown program verification system based on, Hoare logic and theorem proving and all that kind of stuff. The language Spark is actually a subset of Ada 2012, and it uses contracts. The other big thing about it is it's got contracts embedded into its core. So we have preconditions and postconditions and assertions in the language, which are used by the proof tools to prove things about your code. So what I decided to do was to rewrite TweetNACL from the C original into Spark and then see if I could prove stuff about it. And see, for example, if I could prove it would never crash or never raise an exception. We call that, posh, flashy programming language people call this type safety or memory safety. It basically means your program never crashes or never raises an exception and never kind of goes nuts. It never has an undefined behavior, which, things you don't want to happen in your program. So I tried to do that and, I'll fast forward a bit and I was successful. I managed to get this to work and then prove it was really type safe. And the proof is also automatic. You just press the button and the proof tool grinds away for a couple of minutes and then says yes. And it's proven something like 1,500 verification conditions that show the code basically is kind of bomb proof and can't do anything stupid. And I also proved some correctness properties of the mathematical stuff en passant. I had to prove a few correctness things as well while I did it. So that all went well, and that was about 9 months ago. And then much more recently, what I tried to do was to actually test it for performance to see if the formal Spark code could actually match the C in terms of execution time efficiency, because that matters to people with particularly cryptographic stuff. You want it to go pretty fast. So I wanted to see how that would come out as well.
Did it match it?
I'm pleased to say eventually the answer is yes. Initially, the Spark code was a bit slower than the C, and that's not unsurprising. There are certain things about Spark. Spark, for example, for proof, Spark rewards a more functional programming style. If you're used to programming in something like Haskell or ML, this won't sound surprising. It's very elegant to employ a functional programming style. That comes with a certain penalty in terms of execution time because we tend to be copying data from one function to another a bit more. But it wasn't that far off, and I was quite surprised. So I then set about doing quite a detailed analysis of the execution time and seeing how I could improve it by doing some transformations on the code, if you like. And while I did that, for every transformation that I made, I was running the proof tool to make sure I hadn't made a mess of it. And the proof tool, my basic golden rule was that whatever I did to the code to make it faster, the proof tool had to check it and tell me everything was fine. Otherwise, I wouldn't do that transformation. So I kept proving it over and over again every time I fiddled with it. And there was basically a bunch of tricks that I did. And having concluded that work now, the Spark code is actually running appreciably faster than the C. And that's quite a surprise because because of some mathematical tricks I was able to exploit. We've actually got it to be quite a bit faster now, which is quite nice because people tend to assume that this formal stuff is great, but it's too slow. And people come to us and say, we'd love to do Spark, but no, this code has to go really fast, so we have to write it in C. And the answer to that is, nah, you can get this stuff. This formal stuff can be really fast. In fact, it can be faster because the programming language has certain intrinsic properties that make it it's highly amenable to optimization. The optimizer in GCC, for example, looks at Spark code and says, this is nice and simple. It's got all these lovely correctness properties. Great, I can optimize all these function calls. So, for example, all that function calling and returning and copying overhead actually all disappears because the functions don't have side effects and there's no aliasing in the language and so on and so on. The compiler takes advantage of that and actually generates really cool, efficient code, which is a really nice kind of synergy of the formality and the compiler technology working together.
That's an amazing kind of result from all of that. And what's interesting, well, there are some benefits you get by just using Spark. Mm-hmm. And then there's benefits just going all the way back to specification. Since it's a constant and it's not changing, mm-hmm. you can do those optimizations without worrying in a way. So you can really dive in and then you have this prover just checking constantly and telling you, hey, you've actually ruined it or not.
I mean, in 20 or 30 years of programming, is it 30 years? It's more like 40. I've been programming for nearly 40 years. So starting in my bedroom as a teenager with a home computer in the 1980s, I learned to program in assembly language. I have an acute understanding now of how brilliant I'm not as a programmer. And knowing that this proof tool is kind of saving my bacon all the time, because it spots mistakes in what I'm doing and helps me prove that I haven't made mistakes, with checking that the types are all still okay and it's not overflowing and I haven't introduced a buffer overflow or whatever. It's really nice to have that tool backing me up. And this kind of proof-based refactoring, we call it, is a really interesting concept because the proof obviously is just in a team-based software environment. If we're working in a big team, obviously we have a continuous integration kind of thing going on where the continuous integration stuff is continuously checking the proof of the software all the time, and knowing that proof is always going to happen for every single change gives you a real sense of confidence that you've not introduced some egregious stupid mistake. And you get the feedback within minutes, on a decent computer these days. That proof tool is going to come back and, point out your mistake within a matter of seconds or minutes of you doing anything. And that's really, really nice to know. So it's a really nice way of working. And something when we're doing this stuff with big teams, it just becomes normal practice. All the developers do the proof stuff all the time, and that's just standard discipline for the teams working on the big projects with Spark all the time now.
This gives a really different perspective in when we look at adding formal methods to a project or having formal methods in a project and writing mechanical specs. What a lot of people might hear is that it's going to be something that holds them back, and that every time I want to do something, I'm going to need to worry about the proofs. It sounds like when applied correctly, such as in this situation, yes, you did need to write the proofs, but in the end, it really liberated you and let you try things that you would have maybe been afraid to try otherwise, or that trying would have been prohibitively expensive in the sense that you would have had to heavily create new tests every single time you made a speculative performance change to your code.
Yeah, I think that particularly, some of the transformations I did in the NACL implementation were really quite risky in terms of things like changing the layout of data and squishing data into fewer bits than you would have otherwise, and things like this. These are changes where you could really easily make a mess, and the proof tool just saves me from getting that wrong, which is really, really nice. And I using Spark, I have that confidence, and I am acutely worried if I have to write C and I know I haven't got that kind of technology backing me up. I'm acutely aware of how error prone I am writing code. So it is a nice feeling. And I mean, you talk about writing proofs, and that's not really what well, it kind of is and it isn't. What I'm writing is source code. Remember, all of this proof stuff is automated. I just push the button and it runs. So what I'm really writing in the code are things like preconditions and assertions to say, at this point in the code, this should be true. So what we do on Teams is we say to people, well, the proof has to run, but be fully automated. It's got to just run on its own on the machine. There's no kind of maintaining a proof script or a sort of different artifact for the proof. It's either got to be fully automated or it's not right. So with big teams, we set a target. We say to people, well, 99% of your proofs have to be fully automated or you don't commit your code. So we set a target for automation that the teams need to hit, and then they get into the habit of hitting that target. And when they hit 99%, we turn the dial up. We say, okay, now it's 99.5, and we go a little bit further. And on some projects, it hits 100. And once it hits 100, we stay there. Once you get complete automation, we just say, right, that's it. We're staying automated. Everything proves every time, or you've broken it. And if you break it, the answer is to write a simpler program. That's usually what you need to do. If you've written something that the prover can't handle, it's probably too complicated, which means it's probably wrong anyway. So go back and write a simpler program and the proof system will handle it and it's okay again. So it's a nice way of looking at it's a different way of looking at the problem. But we found it works very well.
And this sort of circles us back around to your original point, which is, while some people might hear write a simpler program as write a slower program, the reality of the proof tools is that the simpler program in the end might also end up being faster, which is maybe counterintuitive, but it sort of requires an understanding of compilers and what compilers work well on at the end of the day.
Yeah, and when I say simpler, I don't necessarily mean lacking functionality. That's not what I mean. I mean, a program can be perfectly simple, but it can be structurally simple or easier to understand or easier to prove in a way that, you get all the functionality you want and possibly more performance because the compiler can take advantage of simplicity. That's a good thing. And some famous engineer once observed, simplicity takes work. It's not easy to be simple. Sometimes achieving simplicity actually requires a bit of thought and a bit of energy to be put in. And that can be a really good thing. So it's an interesting exercise, if you like, to kind of simplify your software to the point where the proof tools will really do well on it. Is an interesting exercise.
So all engineers want formal specs. All engineers likely want to be writing simple programs at the end of the day, but the realities of the day-to-day demands on engineers often pull them away from that direction. And what I'm hearing a bit about tools like Spark is that they serve to pull engineers back in this direction of, in a sense, where they wanted to be in the first place, which is writing simple code and writing code that is doing a well-defined thing. Is that an accurate statement?
Yeah, that seems perfectly reasonable to me. And yeah, the tools do keep us honest. It's, I don't curse anymore. When the tool spots a mistake in what I say, in what I've done, I don't curse the tool. I say, oh, thank goodness it spotted that mistake. And that means I'm not burdening that mistake on one of my colleagues who has to spot it by reviewing the code and I have to fix it later or something. If the tool tells me I've got it wrong, I fix it immediately and I think, phew, that was good. It saved me again. And I like that a lot with the tool. If people are interested, the Spark NACL code is on GitHub. In my account, I've released it. It's permissively licensed, so you can see. And actually, in the GitHub repo, you can see the steps of the simplifying transformations that I made, if you like, to get the performance out of it. For example, you can see all the commits to the GitHub repo that show how I changed it through various stages. And there's a blog entry I wrote recently about how I did it, if you like, that kind of goes into it. So if you want to see a bit of really well, what I would say, anyway, I would say that obviously, if you want to see a bit of really well-written Spark code, go and look at the Spark NACL sources and see how it fits together. Because it's I'm pretty proud of it. So I don't mind if people want to have a look. I'd be all right with that.
Yeah, we'll definitely include a link to both of those things, actually. I'm sure a lot of people will want to look at it.
That's about the end of the time that we have today. Thank you so much for joining us, Rod. It's been a wonderful discussion.
Okay, thanks very much for the chance to chat today. I really appreciate it.
Thank you, Rod. This was another episode of Building Better Systems. We'll see you all later.